our notation. Of course, there are two special log functions. Two special log functions. And they are so special that they have their own key in the graphing calculator. Where's my calculator? Right here. Same thing, key with e to the x. It's this one, ln. So they must be related, and they are. They're inverses of each other. And another one is log, and related to 10 to the x. And how they are related, they're inverses of each other. So the two special functions are f of x equals log x. And you can say, I don't see the base. By convention, log has no base, which means base 10. That's why, so this is base 10, and this is called common log function. So log x is common log function. Of course, there is another one. Which one? With which base? E, Euler's number. So this one will not be log, but it will be denoted by ln. So f of x equals ln x, named natural log function. Special, again, right here, it has its own key. Of course, related to e to the x. Okay, one thing I have not convinced you yet. I have not convinced you that the inverse function of the exponential is the log. I have not convinced you yet. So give me an exponential function. I want to convince you. And give me three numbers, and one should be positive, and one should be negative, and one should be 0. Any function, any exponential function you want to choose, and three numbers, one positive, 0, and negative.
2 to the x, 4, 0, and negative 1.
Perfect. Is 2 to the x an exponential function? Okay, perfect. So now let's determine the corresponding y values. When x is 4, 2 to the 4th power is?
6.
Perfect. When x is 0, y will be?
1.
Very good. And when x is negative 1, y will be?
1.
1/2. Very good. So now what do I have to show you? It's okay, I know it's late. So what do I have to show you? That there exists a function that is the inverse function of this, 2 to the x. Can you guess which one would it be? And if you say natural log, you will be wrong. If you say log base 5 of x, you will be wrong. But you will have to say log base. Indeed, it must be the same base. It's like I'm giving you $10 and I'm taking it back. If I'm giving you 10, but I'm getting back 5, I didn't cancel the transaction. I cancel the transaction if I'm looking at 2 to the x and I'm canceling it with log base 2, not with log base 3 or 10 or any other base. Right? I'm giving you 10, I'm taking 10 back. If I take less, there is a change in x. Perfect. In order for me to show you, what do I have to show you now? I have to show you that if I apply log base 2 to 16, the answer must be
4.
Indeed. If the answer is not 4, this cannot be the inverse function. Then I have to show you that log base 2 of 1 will return exactly what?
0.
0. If it does not return 0, this is not the inverse function. And finally, I will have to show you that when I apply log base 2 to 1/2, the answer must be, if it isn't, this is not the inverse function, right? Okay. Before I do this, with your help, we have to learn the most important, very, very important concept in this entire chapter. The most important concept in this chapter is this. First, let's write it in plain English. Any log equation can be, and you'll tell me the word you want, translated into, replaced by, converted into, what do you want? Replaced by? Okay. Replaced by an exponential equation, comma, and vice versa. Any exponential equation can be replaced or translated into or converted into a log equation. Okay, that's in English. So now let's write this in math terms. We're going to use this till the end of this chapter. The most important concept. Log base a of x is y. What type of equation is this? Is it quadratic? Is it exponential? Is it absolute value? Is it radical? No, it's log equation. This is the double equivalency symbol, which says I can change this into this and this back into this. Now please follow through, because this is very important to remember or understand from the very beginning how we change the log equation to an exponential one. The base, counterclockwise, the base raised to y equals x. The base raised to y equals x. What type of equation is this? A quadratic, log, exponential. So, when we are given a log equation, if it's more convenient to solve the exponential one, we will change it. If we're given an exponential equation and that's not easy, I'm going to change it into a log, it may be easier. Okay, so why do I need this? Because I need to show now that when I apply log base 2 to 16, log base 2 log base 2 of 16 is a number. I have no clue what it is, but I know that I can change this into an exponential equation. 2 raised to unknown equals 16. 2 raised to unknown equals 16. What is this number? And there is only one number that works. It's 4. So we showed that when we apply log base 2 to 16, we get back 4. Next, log base 2 of 1. Unknown, have no clue. So this is equivalent to 2 raised to unknown equals 1. 2 raised to which number is 1? And there is only one correct answer because the function is 1 to 1. Indeed, 0. So this must be 0. So I go back. We showed that log base 2 applied to 1 returns exactly what? 0. Last one, log base 2 of 1/2. I have no idea what it is, but I know that I can change this into an exponential equation. Base raised to blah equals 1/2. Base raised to unknown equals 1/2. Remember, to change a number into a fraction, the exponent must be negative. Awesome. So what will be the answer in this case? Negative 1. Only 2 raised to negative 1 is 1/2. So we showed how this works. Now, also you can say, what is the log? The log is a power. A power? Yes. A power that I raise the base to get this number. Okay. Let's look at on page 490. What did we say about the log function? And the even index radical functions, and also rational functions. What do they all have in common? Log is not friendly. Even index radical functions like the square root and the fourth root, not friendly. Rational functions, not friendly. Why?
X can be
They have restrictions. Yes, the domain is not all real numbers. Domain is not all real numbers in general. I wouldn't say for all of them, because there are situations in which it can happen. So I'm going to say in general. The best way to remember this is I have to worry about these. I have to study their domain. So that's my next step. I would like to study the domain of a couple of log functions. So let me remind you the graphs. If the base is greater than 1, the graph is this. If the base is less than 1, the graph is this. One more time. What is the domain of the log function? Log has domain pure log. No transformations. Pure log. Has domain. Look at those graphs. It's the range of the exponential. Always. So remember, log cannot be applied to 0, and it cannot be applied to negative numbers. So let's find domain for a function in 77 on page 490. F of x equals log of 2 minus x. The question is only asking us to find the domain. We are not doing anything to the function. We have to state something, solve that, and then find the domain. So, what do I have to write? What is log applied to? In this case, let's read it. 2 minus x. Log is applied to 2 minus x. Log of 2 minus x. What type of number should 2 minus x be for log to exist? Exactly. Exactly. That's the only condition we have to write and solve. For this log to exist, the quantity that log is applied to, which in this case is 2 minus x, must be a number greater than 0. Okay, that's all I need to do. Just solve, moving 2 to the other side, and divide by negative 1. So then what happens next? Perfect. So then the domain of this function is negative infinity 2. Now I would like to graph this function using transformations. Now let's identify whether it looks like this or it looks like this. What is the base? I don't see the base.
10.
Good. So if the base is 10, will it be this shape or that shape? Right. This one, right? Because it's increasing on all its domain if the base is greater than 1. Awesome. So the only transformation, so what is the base function here? Log x. The only transformation is log 2 minus x. So maybe we should break it down into two parts. So let's graph in first log of negative x, and then 2 log of negative x plus 2. I think it's better than just writing it in one step. Okay, so we're changing x into negative x. What transformation is that? Flipping, so x and negative x. It's a reflection with respect to the y-axis. Very good. So number 1, reflect with respect to the y-axis. Number 2 will be log of negative x plus 2. So careful. The domain is negative infinity to 2. The fact that we had to flip and then add 2, it's basically not something we've done before, but the transformation in this case after a flip with respect to the x-axis, and also remember this is a domain. In this particular case, it was not going to be a left 2, but a right 2, exactly. Right 2. So let's graph. And then I would like to talk about the properties of log. Okay, so here is log x, and it crosses at 1, 0. Then you told me to reflect this graph with respect to the y-axis. Okay, so give me the indicator. Where will the indicator go? Negative 1, 0, very good. So this is the graph of log of negative x. Can anyone give us the vertical asymptote for this function? Perfect. And now the final step, we are moving the green graph to your right too. But there is a vertical asymptote at 0. What do I have to shift first? The vertical asymptote. Where am I shifting it to? To your right. So right here. And now the indicator, which is now at negative 1, 0, where will it go? This was at negative 1, 1. Exactly. So this is the final graph. F of x equals log of negative x plus 2 or 2 minus x. Any questions? Any questions? Any questions? Let's look at just one more domain. Just want to make sure that this is clear, and then we'll look at word problem. 75 on page 490. So f of x equals log base 5 of x plus 4. I only want the domain. And then we'll look at an application here. What do I have to write? Let's write for everyone to see what we need to write that will give us a domain. We have to write that I just have to write exactly what we wrote before. Identical situation is just that it's a different function. What do I have to write? Yes, indeed, x plus 4 greater than 0. This quantity has to be positive, otherwise log does not exist. So then x greater than negative 4, so the domain of this function is? Perfect. Let's look at a word problem. And here are the options. and you choose. We want to see what students in psychology did on a test. We want to look at a function that models the wife's weekly housework hours.
Psychology students.
Okay. Very good. So let's read the problem. Students in psychology, in a psychology class, took a final examination. As part of an experiment to see how much of the course content they remembered over time, they took equivalent forms of the exam in monthly intervals thereafter. So they took an exam now, and then a month later, 2, 3, 4, a year later. The average score for the group, so this is problem 119 on page 491. We are given f of t, average score for the class or the group is 88 minus 15 natural log ln of t plus 1, and we are told t is between 0 and 12. After t months was modeled by this function, t in months. What was the average score on the original exam? That's part A. Part B, what was the average score after 2 months, 4 months, 6 months, 8 months, 10 months, and 1 year, and then sketch the graph with a graphing calculator. So in part A, we want to determine what was the original score. Not after 1 month, or 5, or 6, or 12, but the original. What does that mean? Exactly. T equals 0, and we're going to plug it in. Then we want to find f of 2, and then f of 4, they say, and then f of 6, and then f of 8, and f of 10, and f of 12. That's what they want, and then look at the graph. Of course, I'm going to plug in the function. I don't want to do this, 7 times. So in y equals, let's go to y equals. Clear if you have anything else in there. And let's write 88 minus 15. Natural log is right here, ln, parentheses, x plus 1, and close the parenthesis. There is no n in the graphing calculator, so I have to replace it by x, or t. Okay, so what numbers do I want? Well, I want 0, 2, 4, 6, 8, 10, and 12. So second in table, 0, 2, 4, 6, 8, 10, and 12. So what was the initial score so I can put it in? What was the score after 2 months? The average score, 71.5. What was after 4 months? 63.9. After 6 months, 58.8. After 8 months, 55. After 10 months, 52. And after 12 months, 49.5. What do you notice? Yes, it's definitely decreasing, right? So what we know today, it's fresh in our brain, and a month later we'll know less and less and less, and 12 months later. Okay, so let's graph this function now. Now I want to establish the viewing window. So what is the viewing window on the x-axis? What should it be? Of course, 0 to 12, right? That's all we have, 0 to 12 months. So in the viewing window, I will put 0 to 12 with a scale of 2. And now let's think in terms of the y-axis. How far low do I have to go? Let's say we want to see the x-axis. So I want -4. But how high do I have to go? Definitely above. Yes, definitely above 88. Correct. So I'll say -4. I'll say 100. And let's say a scale of 20. And now I press enter. And here's the graph. It's coming from 88, decreasing till about 50%. So that is the graph of the average scores of this psychology class over the time span of a year. Any questions? Any questions? Okay. I know I'm down to 10 minutes. I just want to move on to 4.3 just to give you the 3 properties. 4.3. Properties of log. The log has 3 properties that no other function enjoys or has. Only log. Here it is. Log of a product in any base. I'm going to write base A. Anything. Not 0, 1, or negative, though. Or either between 0 and 1 or greater than 1. So this is what it's called the product rule. And this is log base A of the first factor plus log base A of the second factor. If I have 5 factors, it's going to be log of A plus log of B plus log of C, and so on and so forth. So here's an example. Log base 3 of 3x. This is log base 3 of 3 plus log base 3 of x. Let's see if I can determine this. I cannot determine that because I don't have x. But let's see if I can determine this. Log base 3 of 3, I have no clue. But I know that this is equivalent to 3 raised to whatever equals 3. 3 raised to whatever equals 3. What can this be? 1. Only 1. So the answer simplified form is this. So this is what the property, one example, one application of the property. I can simplify. So this is the product rule. I want you to remember that this is dynamic in the sense that I can have the right-hand side to change it back into the left or the left to change it back into the right. So let me give an example going backwards. So let's say I have log base 5 of 2 plus log base 5 of 10. Of course, they have to have the same base. Then I will say this is log base 5 of 2 times 10. Good. Here's the second property. Log of A divided by B in any base. What do you think? Just a wild guess. What do you think this would be? Say it again. The difference. Exactly. So this is the quotient rule. And this will be log base A of A and minus log base A of B. Of course, it goes back and forth from left to right and from right to left. So let's look at an example. Log base 3 of 20 minus log base 3 of x. Can I condense this in any way?
Log base 3 of 20 over x.
Exactly. So notice one thing, a very important thing. If the log has a negative in front, its quantity, it's coming from the denominator. If it has positive in front, the quantity is coming from the numerator. Last property. Log base A of x to the nth power. This is the power rule. Here's what we do. we bring n down as a factor. It multiplies. N times log base A of x. Back and forth, though, meaning if I have log base 5 of x squared or cubed, what will I write? What can I write? 3 log base 5 of x. What if I have negative 2 natural log x? So when a log has a number in front, this number in front comes from the power of the expression inside the log. So then this is coming from the power of x. So this is natural log x to negative 2, because this is negative 2 natural log x. And x to negative 2, remember this is not a negative number. It could be, but not necessarily, 1 over x squared. I just wanted to choose 2 examples and we'll stop with condensing or expanding. Let's try expanding first. Expanding log expressions using the properties that we just looked at. Here's one. Log. This is problem 27 on page 501. Log base b of x squared y over z squared. With parentheses or without parentheses. They're asking us to expand this into simple logs, applying all 3 properties if we need to. So when we want to expand, the first step is to look at the division. So log applied to a division, meaning I'm applying the quotient rule. So then this will be log base b applied to squared y, very good, applied to the top, and minus, very good, log base b applied to z squared. Awesome, but not enough. So we're done with the quotient, but now I have this, which is a product, and I have this, which is a power. So what do I replace log base b of x squared y by? Log base b of x squared, and then plus log base b of y, and then I'll bring the 2 in front, minus 2 log base b of z. However, I have one more step. This is clean, but this one is not. I have one more property to apply to the first one. 2 log base b of x plus log base b of y minus 2 log base b of z. I want to draw your attention to something. How many quantities? 1, 2, 3. How many quantities are in the denominator? 1. So there is only one quantity in the expanded sequence or expression that has minus in front. How many factors we have at the top? So there are 2 with positive in front because their quantities come from the top. Okay? One more simple one. Let's look at 19. Natural log applied to the 5th root of x. We're asked to expand this. Well, I have to think what power is the 5th root. It cannot be 5 because x to the 5th and the 5th root of x are not the same. So first I will replace natural log by x raised to which power? 1/5, awesome. So the 5th root is power 1/5. There is only one property that I can apply here, which is to rewrite this as 1/5 natural log x. Any questions?